Building massive projects and smart infrastructure, we innovate boldly, connect communities sustainably, and shape a stronger, brighter future together with vision, technology, precision, and purpose. After the steel reinforcement cage is fully installed and thoroughly inspected inside the mold, the concrete pouring process begins. A ready-mixed concrete pump is placed next to the pouring platform, and the pipe is carefully guided to the pouring point by skilled workers. Before starting to pump, the inside surfaces of the mold and reinforcement are inspected to ensure they are clean and free of debris that could affect adhesion. Then, concrete is pumped steadily into the mold through a flexible pipe. Workers control the flow rate to prevent separation and ensure the mixture spreads evenly around the dense reinforcement. The concrete pouring sequence follows a predetermined pattern, usually starting from one end of the mold and progressing along its length. This method allows the concrete to flow naturally around the reinforcement, embedded components, and inserts without creating air pockets. As the concrete level rises, workers continuously monitor the distribution inside the mold. Internal vibrators are periodically inserted and carefully withdrawn to compact the concrete. This vibration process removes trapped air, improves density, and ensures complete contact between the concrete and reinforcement. Special attention should be paid to corners, edges, and areas around pre-installed fittings where incomplete filling can lead to defects. During pumping, the concrete height is precisely controlled to maintain a uniform thickness throughout the section. Workers maintain close contact with the pump operator to adjust pressure and flow as needed. Avoid pumping at excessively high speeds to prevent reinforcement displacement or formwork leakage. Once the formwork is filled to the specified level, the final layer of concrete is leveled and visually inspected for uniformity. Continue vibrating the formwork briefly to achieve proper compaction before the concrete begins to settle. Any surface irregularities are corrected immediately while the material is still easily workable. After the pumping is complete, the pipe is carefully withdrawn to avoid damaging the surface. The filled mold is then left undisturbed to allow the concrete to begin its initial setting process. Once the concrete is set, it is moved to a waiting area for inspection and further steps. At Pier P39 of the Padma Bridge, the installation of pilehead bracing beneath the riverbed is carried out through a carefully controlled underwater construction process. Once the steel tubular piles are driven to the required depth, and their positions are verified, divers and underwater engineers begin preparing the pile heads by cleaning marine deposits and ensuring proper alignment. Temporary guide frames are used to maintain accuracy in the strong river currents. Prefabricated steel bracing members are then transported to the site by barge and slowly lowered into position using heavy lifting cranes. Underwater, the bracing is precisely aligned between adjacent pile heads, forming a rigid structural link that improves overall stability. Divers assist in positioning the bracing plates and ensuring full contact with the pile surfaces. After alignment, the bracing is fixed using high-strength bolts and underwater welding techniques designed for deep and turbid conditions. Special care is taken to monitor joint integrity and dimensional accuracy. Once secured, the connections are inspected visually and with non-destructive testing methods. This bracing system effectively distributes loads, resists lateral forces from river currents, and provides a stable foundation for the pier structure above, ensuring the long-term durability of Pier P39 under the challenging conditions of the Padma River. The installation of the reinforced concrete pavement slabs on the Padma Bridge was carried out with high precision directly over the flowing river below. After the steel truss spans were securely positioned on the bridge piers, the preparation of the pavement began. Precast reinforced concrete slabs were transported to the site by barge and lifted by heavy-duty gantry cranes mounted on the bridge structure. Each slab was carefully lifted into position and slowly lowered onto the supporting steel girders. Survey teams continuously monitored alignment, height, and spacing to ensure the slabs met stringent design tolerances. Once properly positioned, temporary supports held the slabs stable while workers adjusted their final positions. After proper alignment, the slabs were permanently secured using load-bearing joints, anchor bolts, and in-place concrete joints. These joints were then filled with concrete to create a continuous and stable pavement surface. The installation of the concrete slabs was carried out sequentially, one span at a time, ensuring structural balance and safety. Finally, the completed bridge deck provided a solid foundation for the waterproofing layers, asphalt layers, and traffic safety equipment, forming the sustainable Padma Bridge. The material placement process begins with trucks delivering ultra-lightweight foamed glass aggregate to the work zone. The aggregate is discharged directly from the truck beds onto the prepared roadway surface in a controlled manner. An excavator then picks up the loose material and spreads it evenly around the placement area, ensuring full coverage and proper distribution. The operator carefully places the aggregate to avoid segregation and maintain a consistent layer thickness. Once the material has been roughly spread, a motor grader moves in to level and smooth the surface. The grader blade adjusts the height and profile of the foamed glass aggregate, creating a uniform and stable base layer ready for the next construction stage. Temporary struts are installed as part of the Strachan Avenue overpass project to ensure structural stability during construction. Steel strut members are carefully lifted into position using cranes and aligned between supporting elements. Once positioned, the struts are securely connected and adjusted to provide temporary load support, maintaining safety and alignment throughout the construction phase. The production process of tunnel segments starts with the careful preparation of the mold. Each mold is thoroughly cleaned to remove dust, hardened concrete residues, and any remaining release agent from previous production cycles. This step is critical to ensure dimensional accuracy and a smooth surface finish on the final segment. After cleaning, all embedded parts are mounted inside the mold. These components include lifting anchors, bolt sleeves, connection inserts, and alignment elements that will later be used during segment handling, storage, and installation inside the tunnel. Once the embedded parts are correctly positioned and fixed, a release agent is evenly applied to all internal mold surfaces. The oiling process prevents the fresh concrete from sticking to the mold and ensures that the segment can be demolded safely without surface damage or deformation. The next stage involves the production of reinforcement cages. Steel reinforcement bars are cut, bent, and assembled according to precise design drawings. The reinforcement cages are manufactured to provide the required structural strength, crack control, and load-bearing capacity for tunnel lining segments. During assembly, correct spacing and alignment of the reinforcement bars are carefully checked to ensure full concrete coverage and long-term durability. Once completed, the reinforcement cages are transported to the casting area. The cages are placed inside the prepared molds and securely fixed to maintain their exact position during concrete pouring. After final inspections, the mold is closed and locked to form the correct geometry of the tunnel segment. Concrete production is carried out under strictly controlled conditions to achieve consistent quality. The concrete mix consists of dune sand, washed sand, and gravel, all carefully selected to meet specific grading and cleanliness requirements. Dune sand improves workability, while washed sand and gravel provide strength and stability to the concrete structure. Steel fibers are added to the mix to enhance tensile strength, improve crack resistance, and reduce the need for additional conventional reinforcement in some designs. Once the concrete is mixed, fresh concrete tests are performed. These tests evaluate workability, homogeneity, and fiber distribution to ensure that the concrete meets production standards before casting begins. After approval of the fresh concrete, the casting of the tunnel segments begins. The concrete is poured into the closed mold in a controlled and continuous manner to prevent segregation and air entrapment. Mechanical vibration is applied to compact the concrete evenly, ensuring that it flows around the reinforcement cage and embedded parts. Proper compaction eliminates voids and improves surface quality. Once casting is completed, the mold is transferred to the curing area. A steam generator is used to accelerate the curing process by providing controlled heat and humidity. Steam curing allows the concrete to gain early strength within a short time, enabling faster production cycles while maintaining consistent material properties. During and after curing, concrete quality is continuously monitored through laboratory testing. Samples taken from the concrete batch are sent to the concrete laboratory for detailed analysis. One of the key tests performed is the chloride migration test, which measures the concrete's resistance to chloride penetration. This test is essential for tunnel environments where long-term durability and protection of embedded steel components are required. Compressive strength tests are also conducted on concrete specimens to confirm that the required strength levels have been achieved. In addition, steel fiber beam tests are carried out to assess the flexural performance of fiber-reinforced concrete and verify its crack control capability under load. Once the concrete has reached sufficient strength and all quality requirements are met, the demolding and turning process begins. The mold is carefully opened to avoid damaging the edges or surface of the segment. A vacuum lifter is then attached to the segment, allowing it to be lifted safely and evenly without applying concentrated mechanical forces. Using the vacuum lifting system, the segment is transported from the molding area to the pre-storage zone. In this area, the segment undergoes a turning operation, during which it is rotated into its final storage orientation. This operation ensures stability and proper load distribution during handling and storage. The final stage of the process is segment storage. After turning, the segments are loaded onto transport equipment specifically designed for handling heavy precast elements. The segments are then moved to the outdoor storage area, where they are arranged in a systematic layout. Proper spacing and stacking methods are applied to prevent damage and allow easy identification. The outdoor storage area provides additional curing time and allows the segments to reach their final strength. Throughout storage, the segments are monitored to ensure they remain in optimal condition until they are transported to the tunnel construction site for installation. The Rhône-Autobahn A9 project in the Valais region of Switzerland represents a major milestone in modern highway construction. One of its most significant structures is the Gedeckter Einschnitt Rauron, a 1.46-kilometer covered cutting that carries the A9 beneath the town of Rauron. Construction on the GERA began in 2018 following years of planning and involved extensive excavation supported by thousands of drilled piles and reinforced concrete. This engineering solution allows the motorway to pass underground through a sensitive urban area while reducing traffic through the town center and preserving green space above. The design includes a 1,000-meter tunnel section with carefully constructed access ramps linking the highway with the new Visp West and Gampelsteg segments. Works such as perimeter support walls, decking, and paving were completed through coordinated efforts over several years, with major milestones reached between 2020 and 2023. This new stretch of A9 improves traffic flow, enhances safety, and marks significant progress toward completing the continuous Valais motorway network, scheduled for full operation by the end of 2027. The construction of the NAICM Super Balsa represents one of the most important structural foundations of the new airport terminal. At present, the project has reached approximately 20% progress, with 120 concrete slabs completed out of a total of 875, aiming for full completion by August of next year. Each slab measures 20 by 20 meters with a thickness of 1.4 meters and contains around 120 tons of steel reinforcement, providing the necessary strength to support the terminal structure above. Before the concrete is poured, a waterproofing membrane is installed to prevent groundwater from rising above the slab level. Anchors and ballast systems secure the underlying metallic structures, while pumping pits manage water control. This massive slab will function as the lower basement, with the finished floor level of the terminal located 6 meters above. The concrete placement for each slab takes approximately 5 hours, followed by additional time for surface finishing. The specially designed mix includes fly ash to ensure rapid setting, proper curing, and a high-quality polished finish, making the super balsa a key element in the airport's long-term stability. On the east side of Pier 19 of the Padma Bridge, workers are carefully installing an additional protective steel plate to reinforce the pier's structure. The work begins with a mobile crane lifting the heavy steel plate from the work platform. Using lifting cables and precise crane control, the plate is slowly lowered towards the side of the pier. Operators guide the crane operators to ensure the plate remains stable and aligned during the lowering process. Once the plate is in place, workers adjust it into position. The plate is placed flush against the concrete surface of the pier, ensuring full contact along the edges. The alignment is checked to ensure the pre-drilled holes on the plate match the pre-installed fixing points on the pier wall. After positioning, workers begin securing the plate with bolts and nuts. Each bolt is inserted and gradually tightened to evenly secure the plate and prevent deformation. Tools are used to apply the necessary tightening force, ensuring a secure and durable connection. After all the screws are installed, the team of workers conducts a final check to confirm stability, alignment, and safety before completing the job. Once the pre-stressed concrete girders are completed, they are carefully positioned onto specialized, multi-axle transport vehicles designed to carry extremely heavy loads. Each girder is securely supported with saddles and restraints to prevent movement during transit. The transporters move slowly along the designated access routes on the Padma Bridge, following a strictly controlled path to ensure safety and stability. Operators continuously monitor speed, alignment, and load balance as the vehicles advance toward the installation zone. Due to the massive weight and length of the girders, transportation is carried out at a very low speed, often with escort vehicles and signal coordination. Sharp turns and uneven surfaces are carefully negotiated to avoid stress or vibration. Throughout the journey, constant communication between drivers and ground crews ensures precise positioning, allowing the girders to arrive intact and ready for the next construction stage. The installation of the Greystone footbridge was carried out through a carefully planned and tightly controlled construction process. After more than 4 months of detailed preparation, the main installation took place over a single weekend in October. Temporary traffic management was implemented on the M62 between junctions 4 and 5 to allow safe working conditions. Construction began with the completion of a new central reinforced concrete pier, designed to support the bridge structure. A steel pylon was then erected on top of the pier, forming the main vertical element of the symmetrical cable-stayed bridge. Large steel bridge sections, weighing a total of around 100 tons, were delivered to site and lifted into position using heavy-duty cranes. Once the main deck was positioned across the motorway, cable stays were installed and tensioned to stabilize and balance the structure. Additional reinforced concrete works, totaling approximately 200 cubic meters, were completed to secure foundations and approaches. After final alignment checks, finishing works ensured the bridge was ready for use, providing a safe and sustainable pedestrian and cyclist link for over 400 daily users. AMP is developing 4 Ohio River hydropower projects at existing dams, adding low-impact, run-of-river renewable energy for generations with minimal environmental change. The ITD SRTO Port Infrastructure Development Project represents a major investment in strengthening maritime logistics and supporting long-term economic growth. Captured from an aerial perspective, the project highlights the large-scale construction activities required to transform coastal land into a modern, high-capacity port facility with dedicated container yards. The development focuses on creating extensive container handling areas designed to accommodate increasing cargo volumes and larger vessels. Vast sections of land are cleared, leveled, and reinforced to form stable container yards capable of supporting heavy loads and continuous operations. Earthworks play a crucial role at this stage, ensuring proper elevation, drainage, and ground stability across the site. Compacted fill materials are systematically placed to create durable working platforms for container stacking and vehicle movement. In parallel, internal port roads and access routes are constructed to enable efficient circulation of trucks, reach stackers, and other port equipment. These transport corridors are carefully aligned to connect container yards with quays, storage zones, and supporting facilities. Drainage systems are also integrated to protect the infrastructure from flooding and ensure uninterrupted operations during heavy rainfall. The project demonstrates a coordinated approach to port infrastructure development, combining land reclamation, ground improvement, and logistical planning. Once completed, the new container yards will significantly enhance cargo handling efficiency, reduce congestion, and support regional and international trade. Overall, the ITD SRTO project reflects a strategic commitment to developing modern maritime infrastructure that meets the demands of global shipping and future economic expansion. The installation process begins in the laydown area, where the precast concrete girders are delivered, inspected, and fully prepared for lifting and transport. Each girder is carefully checked, rigged, and staged to ensure it meets alignment and height requirements before moving. At the break of dawn each day, transport operations start as specialized Goldhofer modular trailers maneuver the massive girders through tight urban streets. These moves require precise coordination, controlled speeds, and constant communication to safely deliver each girder to the gantry lift location within the confined job site. Once the transporters arrive on site, the next stage begins. The gantry lifting system is positioned over the girder and slowly lifts it from the trailer. With controlled vertical movement, the girder is raised to the elevation of the guideway and placed onto the temporary support system. This step demands exact positioning to maintain stability and prepare the girder for horizontal movement along the elevated path. In the following stage, the girder is shuttled along the guideway toward the launcher, using one of 3 Goldhofer systems operating on the elevated structure. The movement is slow and deliberate, allowing crews to monitor clearances, elevations, and alignment at all times. Once 2 girders have been transferred and fully prepared, the operation advances to the launching phase. During the launching stage, the custom-built launcher extends forward, pushing the girders out over the gap between columns. The girders are carefully lowered into their final position, settling onto bearings with tight tolerances. Crews continuously verify alignment, elevation, and seating to ensure each girder fits perfectly within the structural system. After placement, temporary supports are adjusted to secure the girders before moving on. With the newly installed girders in place, the launcher performs a leapfrog maneuver. It disconnects from the previous set of columns and advances forward to connect to the next set. This leapfrogging process allows the launcher to repeatedly install new girders without the need for ground-based cranes. Below the elevated work, crews install and remove steel support collars around the columns, providing critical stability for the launcher during each move. This sequence is repeated every other day, maintaining a steady rhythm of progress. Despite most activity occurring above ground, constant coordination is required at all levels to manage equipment, supports, and safety measures. As the installation approaches complex areas, such as angled intersections with existing bridges, additional care is taken to align squared and angled girder ends accurately within extremely tight tolerances. When the final girder at the north end is installed, the launching system is partially retracted along the guideway. Due to narrow working conditions and active rail lines below, safety procedures become even more stringent. The launcher is then disassembled in stages, marking the completion of that phase of installation. After a short pause, work resumes to install the remaining girders at the south end. The gantry track is extended to provide sufficient length for staging and launching. With access severely restricted, equipment movement follows a carefully planned sequence to avoid conflicts. One by one, the final girders are launched and set into position. The process concludes with the placement of the last girder, completing the elevated span. After installing a total of 56 girders over approximately 2 months, the launcher and support systems are removed, leaving a continuous concrete guideway that allows uninterrupted rail operations below. The Hillcrest Water Storage Tank Replacement Project is being carried out at Denver Water's Hillcrest facility to modernize critical water infrastructure. The project involves replacing 2 existing 15 million gallon reservoirs built around 1960 with 3 new circular post-tensioned concrete tanks. Once completed, these new tanks will provide nearly 100 years of reliable service. As part of the overall upgrade, the existing pump station will also be replaced to better serve the South and Southwest Denver metropolitan areas. This major milestone includes large-scale concrete placement and reflects Denver Water's long-term investment in system reliability and community engagement. The University of Colorado Hospital expansion set an ambitious challenge, raised the bar once again to deliver a critical healthcare facility under an extremely tight schedule. With an urgent demand for hospital beds and a target of completing nearly 700,000 square feet in just 22 months, the project team was pushed to rethink traditional construction methods. To meet this pressure, they adopted an innovative, multi-trade, multi-discipline prefabrication approach that fundamentally transformed how the building was delivered. Instead of each trade working separately on site, mechanical, electrical, fire protection, drywall, and framing teams were brought together in a single, coordinated prefabrication process. Inside a 50,000 square foot warehouse, complete headwall systems, bathroom pods, and corridor sections were built in a controlled environment using manufacturing-style assembly lines. Advanced virtual design tools enabled precise material takeoffs and seamless coordination between trades, ensuring accuracy and consistency. This approach dramatically reduced site congestion, improved safety, and enhanced quality control through repeated inspections before and after installation. By shifting complex work off-site, the project achieved faster installation, minimized waste, improved sustainability, and delivered a higher quality product, demonstrating how prefabrication can redefine modern healthcare construction. At off-site facilities, complete framing systems and gypsum board assemblies are manufactured to meet the project's exact requirements. The prefabricated framing and drywall components are stacked in the precise order of installation, secured, and shipped to the construction site. Upon arrival, the stacks are unloaded and transported to their designated installation areas. For multi-story buildings, cranes lift the stacked materials to each floor. On-site crews then enter each room and find all walls, ceilings, soffits, corners, and boards pre-numbered and ready. Workers remove each piece sequentially, position it in its identified location, and fasten it securely into place. The Children's Healthcare of Atlanta Arthur M. Blank Hospital showcases a large-scale application of prefabricated construction to improve efficiency, quality, and safety. Many key building elements are manufactured off-site, including prefabricated bathroom pods, mechanical and electrical utility racks, and unitized curtain wall facade panels. Entire multi-trade MEP racks, ranging from 20 to 30 feet in length, are fully assembled in controlled warehouse environments before being transported to the site and hoisted into place. In patient pre- and post-operative areas, nearly 90 prefabricated headwalls are produced off-site, significantly reducing the need for skilled labor on the construction floor. This approach minimizes congestion on a project that employs thousands of workers while also reducing temporary facilities, waste, and logistics challenges. By combining prefabrication with virtual design and construction technologies, the project team achieves better coordination between trades, consistent quality, and faster installation. Overall, prefabrication plays a critical role in delivering a complex hospital facility more smoothly, safely, and on an accelerated schedule. The construction of the ALT Hotel in Calgary's East Village showcases an efficient modular building method using prefabricated units supplied by Modular. The process begins with the transportation of fully finished modules from the manufacturing facility to the construction site. Each module is carefully secured on specialized transport trucks to ensure structural stability and surface protection during delivery through urban streets. Once on site, the modules are staged in a designated area and prepared for lifting operations. A giant tower crane is positioned to handle the heavy loads with precision. One by one, the modular units are connected to lifting frames and slowly hoisted into the air. Crane operators work in close coordination with ground crews to guide each module safely toward its exact installation position. As the modules are lowered, workers align them accurately with previously installed units and the building's structural core. Fine adjustments are made using guide ropes and positioning tools to ensure correct placement. After alignment, the modules are securely fixed together using bolted connections and structural fasteners, forming a solid and continuous building structure. Following placement, workers begin connecting the modules horizontally and vertically, ensuring that floors, walls, and ceilings align seamlessly. Mechanical, electrical, and plumbing interfaces between modules are then linked, allowing building systems to function as an integrated whole. This modular assembly process continues level by level, rapidly transforming individual units into a complete hotel structure. By using modular construction, on-site work time is significantly reduced, safety is improved, and construction progress remains consistent, regardless of weather conditions, demonstrating the effectiveness of modern modular building techniques.